Hey everyone. Okay, so our last lesson in the derivatives unit focuses on Newton's method. Now this is really actually very, very cool. I want to remind you that part of calculus is we are trying to figure out how to solve for things without graphing technology, right? So we're trying to figure out, well, how did they do this before they had a graphing calculator where they could just say, hey, what's the root of this equation? Or hey, what's the intersection of these two lines? Okay, and Newton actually was able to derive a very, very clever way to get pretty exact approximations. And that's what we're going to kind of look at today. So quite often we are asked to determine the solutions to a quadratic equation or roots to a quadratic function, which we can determine by factoring or by using the quadratic formula. Okay, and you guys have been doing that all your lives now. As soon as we move to a polynomial of a higher degree, determining the roots begins to get extremely complex. Now, in 30-1, we did talk about factoring degrees higher than 2. But if it wasn't factorable, we haven't really dived into other ways we could determine those roots. They're not always nice and easy formula to use. Technology would do this for us relatively quick, but technology is a new thing. How did Newton do it 350 years ago? That's what we kind of want to look at today. And as I said, it's really quite cool. And what I'm hoping is I want it to look familiar to you as well. I want you to notice that he's using concepts that we've been using all along. Okay, so thankfully we have a rather ingenious way to approximate the roots of these types of equations. Now, the reason we say approximate here is because we're not getting the actual irrational number like root 7 or whatever, okay? But we are getting a really good and really accurate decimal. Like we can get this up to several decimals long and have it be that accurate. Okay, so here's what we're gonna do. So I've given you just some random graph, okay, and we want to approximate this root. So the first thing we do is we choose a point on the x-axis that's somewhere near our root, and we're gonna call this x1. Label this on both the x-axis and on the curve. So if I just pick a random point and I call it x1, that point as a coordinate pair then, as we've done in other things, would be x1 comma f of x1, right? So I've just picked a random point and I called it x1 comma f of x1, x comma y, okay? Now we're going to create a tangent line from x1. Label that x-intercept of this tangent line as x2. Okay, so here I go. I'm going to create a tangent line, okay? And then I'm going to mark this guy as x2. So that's my x-intercept. Now, is that new x-intercept closer or further from our solution? So again, just to make sure you're aware of what we were doing here, the original x value we chose, I just want to pick, sorry, I'm going to get green ink on so I could keep everything nice and color coordinated. The original x-intercept we chose, okay, that was right here. So the question is x2 along the x-axis, is x2 closer or further to the actual intercept I want? And you can see that it is closer, okay? All right, so create the equation for the tangent line in slope point form. Well, you know that anything in slope point form is y minus y1 equals m times x minus x1, right? That's the equation of slope point form. Now, the question is, I already have a point that I can use. What would I use for the slope? So how could I represent the slope of the tangent line that passes through x1? Well, think about the last month and a half of calculus. The slope of that tangent line is the derivative at x1, right? So my equation becomes, this is slope point form, y minus y1 equals m times x minus x1. I know that my point will be x1 comma f of x1, and I know that my slope will be the derivative at x1. Okay, so just to make sure you follow what I've done, okay, m, my slope, is the derivative right here. It's the derivative of x1. And then the point I have is x1, comma, my y value, which would be f of x1. Okay? Awesome. Now, the other thing I need you to see is, hey, this x2 comma 0, that's also on this line, correct? Okay, it's still on the tangent line because that was the x-intercept of the tangent line that you created. So how could we use that? Well, substitute in our approximate solution of x2 comma 0 and isolate for x2. That's what we're now going to do. Okay, so if I plug in for my x and my y, I'm going to plug in x2 and 0. Okay, so I took the equation I had just established, and now I'm substituting x2 comma 0 for the x and the y. Okay, all right, so now what we want to do is we want to take this formula and we want to substitute, or isolate, I guess I should say. We want to isolate for x2. Okay, all right, so if we were to do that, I'm just going to start in on a new slide. This says the same thing it did on the previous slide. We want to isolate for x2. So the first thing I'm going to do here is I'm going to distribute that guy, okay? And then I'm going to isolate for the term that still has the x2 there. So I have the derivative of x1 times x2 minus the derivative of x1 times x1. So now what I'll do is I will add this guy over to the other side. Okay. And then I can divide everything by the derivative of x1 so that I can get x2 by itself. Okay. And so I've just divided both sides by the derivative of x1. Okay. Awesome. All right. So now I just simplify this out a bit and put it as two terms instead of one fraction, because here I can see that that would just equal 1. So if I separated my two fractions right here, okay, this guy simplifies to just be x1. And then I have minus f of x1 over the derivative of x1. Okay, so here's a way to approximate that x2. Pretty cool. Okay, now that's still not the solution though, right? That got me closer to the solution, but it still wasn't actually that particular solution. So the next question is, well, what if I now took that point and drew a tangent line from there? Okay, so what would occur if we repeated this procedure for x3? Can you guess what the new equation would be? Well, if we go through all that method one more time, take a look at this. x2 ended up being x1 minus f of x1 over the derivative of x1. Well, x3 is just going to be x2 minus f of x2 over the derivative of x2. Okay, so here I go doing x2, getting it a little bit closer, and now looking for that x-intercept, and it ends up being exactly what I just said. Okay, we could just go through that whole process one more time, and we end up with x subscript 3, sorry, equals x2 minus f of x2 over the derivative of x2. Okay, and so we can just keep doing this, and what happens is as we get closer and closer and closer, so like x4 would be x3 minus f of x3 over the derivative of x3, okay? And as we get closer and closer and closer, what happens is you'll notice that the decimal ends up starting to be the same thing. And then we have found the root. We've gotten so close that we're actually on top of the root, and we've figured out an approximate solution for the root, okay? Pretty darn cool. Okay, so what if we continued making even more approximations? What would the equation then become? So the equation becomes x to the n plus 1 equals x to the n minus f of x to the n over the derivative of x to the n. okay? When I'm saying x to the n there, I hesitated there because I don't like saying x to the n. It's subscript n, right? It's not an exponent, okay? It's a subscript. Okay, so that's it. You've determined Newton's method for approximating the roots of a polynomial function. If x1 is a first approximation to a root of the equation f of x equals 0, then successive approximations are given by xn plus 1 equals xn minus f of xn over the derivative of x of n, where n is 1, 2, 3, and we just keep going and keep going and keep going. Okay. Okay. So let's put it into practice so that you can see what's happening. Okay. Determine the third approximation for the root of x cubed plus x minus 1 equals 0, the graph on the previous page, beginning with x1 is 1. Okay, so first thing we have to do is we have to write the equation out and we have to write the derivative. So f of x is x cubed plus x minus 1. The derivative is 3x squared plus 1. Okay, and now we just start plugging the values in. So our x1 is 1. So to get x2, we say x1 minus f of x1. So we just plug in 1 for this guy over the derivative of x1. So we just plug in 1 for this guy. Okay, and so we end up with 1 minus a quarter equals 3/4. Now I can take x3, now that I know what x2 is, right? I can take x3 and do it again. So x3 will be x2 minus f of x2 all over the derivative of x2. So I know x2, I just found that here, so it's 3/4. Okay, I know f of x2, I can plug in 2 for this guy. And the derivative of x2, I plug in 2 for this guy. Okay, so I end up with 3/4 minus 11/64 over 43/16. And I get 59/86. Okay, so the third approximation, that would be x cubed. Okay, the third approximation is 59/86. Now, 59/86 is 0.68604. If I take you back to where that graph was, just going to quickly go back. Okay, look at that. Here was 0.5, and I'm saying it's at 0.686. So that is, based on this being 0.5 and this being 1, you can see that that does definitely look like 0.686 is a good approximation of that. Okay. Okay, so now we're going to try use Newton's method to find the fourth root of 13. Okay, so here's the cool thing. We can use it to find irrational numbers, irrational roots. Okay, correct to 4 decimal places. So here we go. First of all, we need an equation. We need some sort of a polynomial equation that equals 0. Well, if I'm looking at the fourth root of 13, that's the same as saying x equals 13 to the 1/4. Okay, which is the same as saying x to the 4 minus 13 equals 0. Okay, I just took the fourth root of both sides and then subtracted 13. So this is the polynomial equation that I'm now going to use Newton's method with. Okay, so I need to find f of x. Well, f of x is x to the 4 minus 13, and then I need the derivative of f of x, which would be 4x cubed. Okay, so I start with some sort of an approximation. So my initial approximation is going to be x1 is going to be 2. Okay, now I plug it in. So x2 is x1 minus f of x1 over the derivative of x1. Okay, so x1 is 2. That was my initial approximation. And then I'm going to subtract 2 to the 4 minus 13 over 4 times 2 to the 3. When I get that, I have 1.90625. Okay, now I'm going to do x3. And so x3 is going to be x2, which is 1.90625, minus f of 1.90625, over the derivative of 1.90625. Okay, so I just plug that guy into my f of x equation and the bottom guy into my derivative equation. And that gives me 1.898872.125. Okay, and so it says correct to 4 decimal places. Well, I've got lots now to say if I went to x to the 4, if I just did this one more time and I got x to the 4, I've got 1.898828. Okay, so that there would have changed the 4th decimal place. But what I want you to notice, just with rounding, right? Oh, no, it wouldn't have. 8988, 8988, oh, yeah, 1, 2, 3, 4. So that was a 7, and then that was a 2. Sorry, I didn't go far enough in my underlining. So now if I went x to the 5, essentially you just have to keep going in your iterations until that 4 decimal places doesn't change anymore. The fact that it's a 2, it's gone down from like the 5th decimal place has gone down from a 7 to a 2, probably means this is going to round off to 1.8988. But I'm going to do one more and just check. So x to the 5 gives me 1.898. Now look at that. See, it's all the way the same now, all the way to this last decimal. So that's like what? 1, 2, 3, 4, 5, 6, 7, 8. The 9th decimal place is now different, okay, with x to the 5. So now I am sure if I want to write this as 4 decimal places, I am sure that 1.8988 is my accurate answer. It is the correct answer rounded to 4 decimal places, okay? So, oh, sorry, I gotta get my mouse back here. So 1.8988 would be my answer. Okay? You have to admit, somewhere deep inside, this is pretty cool. Okay? All right. Determine the coordinates of the point of intersection of the curves y equals x to the 5 plus y equals x squared plus 1. So now we're not even looking for a root. Now we're looking to solve the point of intersection here. But we're still using Newton's method because what we're going to do is we're going to set them equal to each other because they both equal y, bring everything over to one side so that it equals 0, and then we can use Newton's method to find that root. Okay, so I've got x to the 5 equals x squared plus 1, and then that'll give me x to the 5 minus x squared minus 1 equals 0. So that's going to be my f of x. The derivative of f of x is going to be 5x to the 4 minus 2x. And now I start my iterations, okay? So you pick your initial approximation. I'm gonna pick 1, okay? It doesn't really matter what you pick. It will work itself out as you keep doing approximations, okay? Okay, so x2 will be 1 minus f of x1 over the derivative of x1. I assume you're pausing me with each one of these because it takes a minute to type all this in your calculator. You should get 4 over 3 for that guy. And now I go to the second guy, or sorry, I go to the third guy. So x3 will equal x2 minus f of x2 over the derivative of x2. That's going to give me 1.223997494. Again, pause me. We want to just keep doing this until the number stops changing, right? So pause me and try x3, or sorry, x4. And so we end up with x4 being 1.195607685. Pause me and try x5. Okay, we end up with x to the 5 equals 1.193865388. You'll notice that the 1 and the 9 seem to be stationary now. Okay, x6, please, pause me. You end up with 1.193859111. So we're now the same to 4 decimal places. Okay, try for x7. Pause me. Okay, x to the 7 is 1.193859111. Okay, so now you've noticed I've got 9 decimal places the same. Okay, so this is a pretty darn accurate solution You know, we're down to 9 decimal places now. And so that is the x value of the point of intersection of these two original equations. Sorry, I hesitated there because I had to turn my ink on so I could circle the original two equations for you. Okay, but that's not what the question asked. The question said, what's the coordinates of the point of intersection? So I now need to plug my x value into one of the original and get the y value. Okay, doesn't matter which original you choose. I happen to have chosen the x to the 5. So I plugged in 1.193859111 into that equation, and I get out 2.425299578. And so my intersection is 1.193859, comma 2.425300. Okay. I want you to really stop and think about how accurate that answer is, and you did not use graphing technology. Now, if you think I'm making it up, I'll use graphing technology for a second just to check your answer and take a look. The intersection is 1.19385911 and 2.425299578. Okay. So pretty darn accurate. Okay, now that is where I'm going to leave you. So I've given you homework, and then after the homework on Newton's method, there's also a unit review as you start being prepared, getting prepared for your test. So the next video that we and you will deal with actually will start unit 3 on curve sketching. Okay, in the meantime, if you have any questions, you know where to find me. Take care, guys. Have a great day.